Morning, everybody. Those of you that aren't here chose a bad day to be late because I have toys. Where is it? Right there. Okay. This is a superconductor. This is a little bit. This is not mass spectroscopy, by the way. This is the cold nitrogen. Okay. The Pi Day show was last Friday. It was a week late because of weather. And one of the things they used was liquid nitrogen. Well, they had some extra liquid nitrogen left over. So I brought it. And so what I'm going to do, because we don't get to demonstrate this except maybe once a semester when we have liquid nitrogen, I'm going to use some liquid nitrogen to cool this superconductor down to liquid nitrogen temperatures. That's, was that 72 degrees Kelvin? Something like that, okay? Negative. Hey Siri, what is 72 degrees Kelvin in Celsius? Negative 201 Celsius. So very cold, which is why I'm wearing my safety gear. I'm going to try to dump some liquid nitrogen into this dewar first, and then I'll get it transferred over to the superconductor. I think that this container is mostly empty right now. So I'm going to try to get the lid off. It might be just gas in here. We'll see. But if I did this right, this is not going to spear me in the chest. There we go. Okay, cold. No. That would not be good. Okay, let's see if there's any liquid in here. Might all just be gaseous. Okay, a little bit of liquid. Get that all used up here. All right. So that was that container right there. It's okay, I've got another one. All right, so this is, well, maybe there's enough in there. Let's see. Now we got to get the superconductor cooled off. So it's really small. It's over here on my Elmo. You'll be able to see better what's going on if you look up at the screen. I'm going to knock this off of its little stand here for just a second so it can cool off. Do you see how the liquid nitrogen is boiling away? You definitely don't want to get this on your hands. In it. I would not recommend that either. All right.
Oh, my bad. I didn't remember what the fucking sponge was. I didn't need a sponge. I meant the other one.
All right. Let's see if we can get this to work. Put a little bit more liquid nitrogen in there. I need this thing to be as cold as I can get it and not float. Come on. All right. So let's see if the superconductor is actually superconducting. There it goes. Can you guys see that all right? Okay, so this magnet is currently floating above the surface of the superconductor. Okay? Superconductors have exactly how much resistance? Zero resistance, right? So as you are going to learn, we haven't gotten to this part yet, right? When a permanent magnet has a magnetic field near a conductor, it will push the charges around in that conductor. Normally, there's resistance in the wire and you get some heating and all that kind of stuff. And there's a lag time between what the magnet's doing and what's going on in the wire. With a superconductor, there is no lag time, and so you can get magnetic levitation to happen perfectly, okay? So that thing is floating above the surface of that superconductor. See if I can. I should be able to slide a piece of paper, right? Directly underneath it. So there's no contact there, right? Okay? And it's perfectly balanced because the magnetic field from the permanent magnet, which is the cube, and the magnetic field being generated by the currents in the superconductor are perfectly matching each other. This is called magnetic pinning. That's what this is. And so it will just float there, and there will be exactly zero resistance. The magnet doesn't have to be cold, but now the magnet's very cold. Oh, come here. Right?
It does not like those tweezers.
It's not the tweezers. It's pinning it in the right place on the superconductor. Okay? So there you go. You've seen a superconductor in action so that when I finally get to talk about superconductors, right, I can harken back to this. Yeah?
Is there a way, like hypothetically, to put something that can turn it up to make it rotate more? You know what I mean?
So yes and no. That depends on the strength of that magnet. And that's actually a pretty strong little magnet right there. Okay? So the answer is yes. You just need more magnetic field. But okay. So what do you do when you have excess liquid nitrogen? Kind of want to do a field trip.
Let's do a field trip. Forget the ones that aren't here.
But I only really need to go. Everybody go out into the hallway right here next to the stairs. We want make like a single make a line, like stand all around the walls, but out here on the hard floor. So like go down to the left and just everybody circle around. I'll be there in a second. Thank you. All right. So what we're going to do here Oh, you guys are not going to be able to see. Here, I'll get down. Leave me a big zone right here. So what we're going to see is something called the Leidenfrost effect. Okay, and what the Leidenfrost effect is that the cold liquid nitrogen is trying to boil when it comes in contact with the floor, but that leaves a layer of gaseous nitrogen on the floor, and it will float on top of that layer of gaseous nitrogen. So here goes. It can touch your shoes, it's okay. But do you see how it skitters across the ground? Right? Okay. Let me do it the other way.
It's coming me. It's coming me. Oh,
This really is a good way to clean the floor too. Yeah. Okay. Yeah, and it's like the best air hockey table you could possibly have. Right? Okay. Yeah, like water on a skillet. Okay. That Leidenfrost. It's called the Leidenfrost effect. So if you get a skillet really hot at home and then you splash some water on it, right? It'll be the same idea. You can see it better from that end. No. Who cares about the floor?
the floor set out.
There we go. All done. So there you go. A little bit of thermodynamics too. Come on in. Literally.
Wait, so will it like permanently stay like that?
Till it warms up.
But that would take a while at room temperature, right?
Yep.
Is there like a name for the material?
Yttrium barium copper oxide. Copper oxide.
Like, is there any way to like restore that and keep it, or do you have to toss it immediately when you're done?
The liquid nitrogen?
Yeah.
It's eventually just going to boil off. The doer can only keep it for a few days.
Wait, then you guys keep that on site then?
What's that?
You guys keep that on site?
Well, we got it last Friday. It was filled up last Friday. If you go to a welding supply store, they have it. Like Fresno Oxygen Supply and that kind of, yeah. Fresno Welding Supply, rather.
Oxygen supply is crazy.
Costs about $5 or $6 a liter.
Oh, that's not bad.
All right, what am I going to do with this? Oh, no.
Will it clean the carpet?
No. It'll probably, it does bad things to the glue that holds the carpet down. But, all right. Okay. So lecture is all downhill from here, right? That was peak excitement for lecture. Sorry to say. All right. What were we doing? Oh, wait a second. We had lab yesterday.
We got to the mass spectrometry.
There's a problem in the schedule with the lab schedule. Next week we are having a lab. Force on a wire, I believe. So I think it says next week we don't have any lab. We have lecture. No, we're going to have lab next week. So that is an error. But I believe that your next exam, I know it feels like too early to be talking about the next exam, but we got to talk about the next exam. Your next exam is the Thursday after spring break. I tried to get it before spring break, but it's the Thursday after spring break. I apologize. So just get that into your brain, right? Go have a good spring break, have fun, but we're going to have to recover pretty quickly.
Are we gonna have a review day?
Yeah, we're going to have a review day.
Are we also gonna be?
Like that Monday after spring break is going to be like reviewing and coming back up to speed. Then we'll do the same thing on Tuesday, right? And then we'll take the exam Wednesday. So sorry. I can either go really fast right now and like totally like destroy you, or go with the right pace. Well, what do you want to do? You want to do it before spring break or after spring break? No, we'll stick with the schedule. We'll stick with the schedule. All right. Yeah, it's a benevolent dictatorship. Okay, we were here. This is where we were. And I was showing you that we could select for a very specific velocity. If we could balance the electric force that a charge feels from an electric field and the magnetic force that a moving charge feels from a magnetic field, we set those equal to each other, the path of the charge has to be a straight line, right? Forces are balanced, nothing else is going on. That speed is not on the screen. That speed, ta-da, is equal to the electric field divided by the magnetic field. Electric field in newtons per coulomb and magnetic field in Tesla will get you a meter per second. And so we have our velocity selector, right? This thing that will only allow charges that are moving at that speed to get from one end to the other, because any other charge is going to bend. If it has a speed different than this speed, it's going to bend out of the way. Like, how do we know? So you have a homework problem, a conceptual question that's got a whole bunch of vectors, like 11, 12 vectors on it, right? And it asks you, which of these is going to go in or out of the page or something like that. And they tell you that the speed is either less than or greater than this ratio right here. What will cause the charges to bend up like this? What has to be true if the charge is going to bend up? The magnetic field has to be stronger, right? Okay. And what causes one to go like this? The electric field has to be stronger, right? So again, if this speed, right, is less than this ratio, that means the electric field is going to win. It doesn't have enough speed for the magnetic force to be able to counteract the electric force. It'll go down. But if the speed is bigger than this ratio, then the magnetic field is going to win. And it's going to cause the deflection up. So that's kind of a clue or a hint to that conceptual problem.
So in that same problem, it also asks you to determine which field you're going to use. So if we determine that the magnetic field is larger, we're going to be using.
Then it's determined by the magnetic force, right? And then you do a right-hand rule to see if it's in or out. Yeah, exactly right. Yeah. We set it up that way. We designed our velocity selector to do that. So the question is, why is this field up and why is this electric field down? Right? I just decided that. I could have done it the other way. I could have had the magnetic field down and the electric field up. That doesn't matter. I'd have to flip the directions of these charges and flip the direction of my field, right? But yeah, we're just trying to get a balance of those two. So whatever direction the electric force is pointing, I want to oppose it with the magnetic field force. So I guess the answer to your question is it's arbitrary. I picked it that way. Okay, so now that we have a specific velocity, known velocity of these ions, these charges that are coming into our mass spectrometer, we can take this whole velocity selector, and now I'm going to kind of zoom out a little bit. Here's the velocity selector. Okay? And that velocity selector gets attached to a big chamber. Okay? And inside of this chamber, I'm not drawing this very well. Let's see, we've got charges that are coming in with a known speed v. And what we want those charges to now do is to be, we want them to have something be different because of their mass. This is a mass spectrometer. We want to be able to distinguish the masses of these charged ions that are coming into the device. So how do we discretize, or how do we connect this to something that's got mass in it? Well, Newton's second law does exist. I side because it's Newton's second law with all the horrors and things that come along with it, right? Okay. But if I take a charge moving at some speed and I put it into a magnetic field, say a magnetic field that's pointed out. According to the right-hand rule and the Lorentz force law, what's going to happen? We talked about this earlier. When a charge moving in a straight line enters a magnetic field, what is its path going to be? Remember, it's going to circle, right? It's going to start going in a circle. As this charge enters the top of this chamber, moving to the right, I would shake my hand to the right, and then I'd rotate my wrist so that my fingers came out of the screen, right? And which way is my thumb pointed? Down. Well, okay, so it gets deflected down. Finger's still out of the screen, right? Do you see how my thumb is always pointing towards the center of an arc? Okay, so this charge is going to move. Oops, let's do this in red. This charge is going to move in an arc like this. Okay, it's going to experience a magnetic force towards the center. Now, be careful. This is a different field, a different magnetic field than the one that was in the velocity selector. We have two different magnetic fields going on now. Okay, I'm going to call the one inside of the mass spectrometer B prime, just to call it something else. Right? It's not a derivative. It's all those math teachers that have ruined you. You can tell Mr. Woods that. Okay, what have I got? I've got a force that's pointed towards the center of this arcing path, otherwise known as a centripetal force. And does anybody remember the relationship between centripetal acceleration and velocity? V squared over r, isn't it? So I can go ahead and write this as mv squared over r. And the only force I have is my qvb prime. That's the magnetic force. The centripetal force acting towards the center. Okay, something cancels on both sides. What is it? One of the v's, isn't it? So that makes that easier. I can rearrange this. mv over qb prime is equal to the radius of that circle, isn't it? By the way, the thing in red isn't just for a mass spectrometer. This is the radius that any charged particle will take in a magnetic field. If you know the charge's mass, you know how fast it's going, you know the charge on it, you know the magnetic field, you can find the radius that it will circulate in that field.
Is the blue B prime, is that just saying like all the things that are coming out?
Yeah, I just said it's coming out so that thing would curve down. I just want to distinguish it from the other B I have on the screen over here. Where's the purple B? Where does it exist? Only in that velocity selector. I drew a big version of the velocity selector over here so we could see what was going on. But the velocity selector, in truth, is very tiny. Yeah, a little tiny thing up there where the purple V is coming out. That's the velocity selector. Okay? But that box in red, independent of a mass spectrometer or velocity selector or anything, any charge moving in a magnetic field is going to circulate with the radius given by that equation right there. And you have a couple homework problems that have circulating charges in it. All right, so for the mass spectrometer in particular, what we want is mass, right? Our mass is going to be equal to R times the charge times the magnetic field in the machine divided by the speed that it's going. But we know the speed that it's going. What speed is it going? electric field over magnetic field from the velocity selector, right? So RQB prime all over E over B, so there's another B that comes up, and our electric field's right there, right? So what we have here, we can figure out the charge, okay? Is that true? So usually, I made a little tiny mistake. I'm going to move this Q back over here. The mass spectrometer gives you the ratio of the mass to the charge. It's really hard to tell if something is singly, doubly, or triply ionized after it goes through its process of being blasted into its molecular components. So often a mass spectrometer will just get the ratio of mass to charge. And then we know, because we set it up, we know the magnetic field inside the mass spectrometer. We know the magnetic field in the velocity selector, and we know the electric field in the velocity selector. Those are all determined by the machine, and we're in control of the machine for now. The only sort of dependent variable we have here is the radius. So the bigger the mass, the bigger the radius it's going to be. So as charges come through, some of them will do little arcs, some of them will do medium size, some of them will do bigger arcs. And if we put a detector over here that measures the distance from the velocity selector, effectively gives us the radius of that charged particle's motion, we have a way of telling the different masses that are coming through that velocity selector. Something that's got a bigger mass, it's going to have a bigger R, right? And the machine can calculate it for us. Little tiny masses, things that don't weigh as much, molecules that are tiny, will come through and do that, right? So that's where, see how they've, on their mass spectrometer here, right? The mass per charge in chemistry, Z indicates like proton charge or something like, mass per atomic number or something like that, right? Okay. So what this is telling us, little tiny red dots are like, there's very few things of this mass coming through, right? But there's a whole bunch right there, okay? Apparently glucose is made of a whole bunch of something, some molecule, right? That is that mass per charge right there. And like I said, if you have other white powders, you're going to get different signals because of the different chemical constituents that are made up in there. So even though I was talking about the mass spectrometer, this really can be applied to the circulation of charges in any magnetic field, including the Earth's magnetic field. And when charges circulate in the Earth's magnetic field, they end up giving off energy. That energy tends to concentrate within something called the Van Allen belts that exist around the Earth. Van Allen, last name of the guy that postulated and went and measured and discovered that they were there. The Van Allen belts are highly ionized, and it's dangerous for spacecraft to fly through them. Luckily, they're pretty far out there in terms of like where we need satellites to be to do GPS and things like that. The other place that particles in the atmosphere tend to congregate are around the north and south poles of the Earth. That's where field lines are coming out and going into the Earth. And so a particle from the sun will interact with the Earth's magnetic field, start to rotate around field lines, and it will have a component of its velocity that will take it in one direction or the other. And when those charged particles slam into the Earth's atmosphere at the poles, because that's where the field's coming out or in, you get the aurora. You've probably seen pictures of the aurora. Those are charged particles from the sun captured by the Earth's magnetic field, rotating around and moving in helical paths. So there's that rotation around the field line, but they also have a velocity that causes them to do like a helix motion around the field lines. My master's work was developing telescope coatings so that we could take pictures of the charges that are trapped in the Earth's magnetic field and be able to do something called space weather. So to be able to predict what the Earth's magnetic field would do in response to solar storms, and solar storms directed at us. Right now, the solar cycle is in a very, very active state, There's an 11-year cycle of min to maximum solar activity, and we're peaking this year. And so over the next 11, 12 years, it's going to be kind of dying off to a solar minimum. But we have auroras all the time, but we tend to have a lot more intense ones when we're at a solar maximum.
It makes perfect sense you'd want to be a space meteorologist.
You're welcome. I'm not going to talk about the Hall effect. I'm going to move on because we played with superconductors instead. Short version of the Hall effect is that we can actually make a magnetic fieldometer. We can directly measure a magnetic field based on a potential that exists across a conductor, but you can read up on it. It's not that. Sometimes the reason I talk about the Hall effect is because in video gaming nowadays, you can get Hall effect sensors in your joystick. They're supposed to be better. Frames win games or whatever.
It's that they last longer.
Yeah, it's just there's no moving parts to break. It'll break when you throw the controller instead. What chapter did we do? We just did chapter 28, right? Okay, let's do chapter 29. Let's get started. But yeah, Hall effect sensors it's not the fact that the Hall effect sensor is better. It just means that there's no moving pieces like that can wear out in the sensor. There's still springs in there that can wear out. There's still lubrication that can wear out. So it's not going to last forever. But it is a better sensor just like a brushless motor is better than a brushed motor. It's not going to wear out as fast. All right. So far, what we've talked about are single charges in magnetic fields. And then we extended that to the force that a current carrying wire would feel in a magnetic field, because a current carrying wire is just a train of charges that are going along, right? So we can add up all of the charges together, call it the current, and we had ILB. So last chapter was focusing on the forces that currents and charges experience because of some external magnetic field. It's being generated by who knows what, right? A permanent magnet or the sun or the Earth's magnetic field, whatever the external source was, we never explained where the magnetic field came from. Now we're going to explain where the magnetic field comes from, okay? And we're going to start with wires. Historically, it was the magnetic field around wires that really got scientists thinking about what the magnetic field is. Of course, iron-bearing rocks had magnetic fields associated with them, and that was it was a mystery, it was a sideshow, it was a magician's toy, it was a lot of things, but scientifically, they didn't really have any good explanations for what was going on there. It just was. But as they started to realize that current carrying wires caused magnetic fields, we started getting into where magnetic fields really come from. So what I want to do is I want to play some videos. Oh, computer, why do you always do this to me? Forever, ever since the last update, it always opens these on the wrong thing. All right, let's do this video. Okay. I'll narrate again. Well, let's see if the audio is working.
We'll use these wire forms and some iron filings to show the shape of the magnetic field around various current-carrying wires. This is a simple straight wire arranged vertically. We'll turn the current on and sprinkle filings around the wire to show the shape of the magnetic field.
So you were doing this a little bit yesterday in lab with permanent magnets, right? What they've got is a current that is flowing down that wire. They've got a better shaker than we do. But do you see what the iron filings are doing?
Here are two wires carrying currents in opposite directions.
Right, 2 circles around each wire.
This is a 5-turn loop of wire.
Yeah, now nothing's working. So that looks like a bar magnet, doesn't it?
Here is a solenoid.
Wow, now the video's cutting out. Right? And I told you not to put the iron filings on the solenoid. But you guys got the picture of that, right? In your labs yesterday. So what's the moral of the story? What do current carrying wires do? They create magnetic fields. So our quest now, the yellow exclamation mark, the quest marker, okay, is go figure out where magnetic fields come from. Quest accepted. All right. Where did it go? I will remind you that you can leave at any time. You're not required to be here, but you did pay to be here, so. But somebody told me I had to. All right. So how do we do this, right? How do we do the magnetic field of a current carrying wire? When we first started this class, week 1, and we started talking about forces, we then graduated from forces to fields, right? We went from the force of charge experience via Coulomb's law into the electric field, right? So we've already done that analog for magnetism, last chapter. We started with force, we did find the magnetic field. So now we need to do kind of what we did in electric fields, where we were like, okay, we know charges make electric fields, but now I want to find out what happens if I have a whole bunch of charges together, like what's the electric field of, say, a wire? What's the electric field of a ring? What's the electric field of a disk? What's the electric field of a... And what am I about to write down? Right? But in order to write down the integral, in order to talk about, so if I'm over here, magnetic field of a current carrying wire, right? I want to integrate, but I need to integrate some little chunk of the field, right? When we did this back with electric fields, right? We were finding the electric field with a little tiny chunk, and we said, okay, well, we're just going to start, right, with little tiny pieces like from point charges, right? We start with a point charge, and we move. What's the point charge? Notice I did not say what's the point. I said, what's the point charge for magnetic field? Okay, good, Lewis, because it cannot be a magnetic monopole, because those don't exist. So it's not like there's a little tiny piece of magnetic charge somewhere, or a little tiny piece that exists. They always exist as dipoles, don't they? And so Biot-Savart, the last name of somebody, okay, probably French, Belgian probably, okay, came up with the little tiny piece, the mathematical description of a little tiny piece of magnetic field, the thing that contributes to it. And this is what he discovered. So again, it's the little tiny piece, right? dB, little tiny piece of magnetic field. It's equal to a constant. And I wish I could stop there. Oh, another constant? Okay, well, it's not so bad so far, right? Times a current. Oh, okay, well that makes sense. We saw it in lab yesterday with the solenoid. We just saw it on the video. We know that current carrying wires make magnetic fields, right? No problem. Problem. It was good for a moment, wasn't it? It was looking good, and then it just completely fell off the rails, didn't it? Quantum mechanics. Okay. Thank you, Amari, for that question, because I really don't want to have to deal with anything else. So let's deal with the constant first, right? What the heck is mu naught? It's a constant. It happens to be the permeability of free space. I had to think for a second. You've seen a similar constant before. When we did the electric field, and we had the electric, the electric field was equal to the force divided by the charge, right? And when we did the point charge, it was KQ over R squared R hat, right? And we did tricky things with R vectors, which we'll show you in a minute. What was K? 1 over 4 pi epsilon naught. What was epsilon naught? It was called the permittivity of free space. And the title is not important. What is important is what it means. Like if epsilon naught is there, what do you know? That the electric field is involved somehow. Even if it's not explicitly like it says, electric field is this. If you see the constant epsilon naught, electric field is doing something somewhere. You just know it. It's a dead giveaway. The permeability of free space, mu naught, is the same idea, but for magnetic fields. If you see a mu naught show up in any formula anywhere, magnetic field is somewhere. Even if there's no B anywhere in the equation, if mu naught's there, you know magnetic field is doing something. So does anybody remember what epsilon naught was? I don't expect you to, but does anybody? Yeah, well, K was 8.99 times 10 to the 9, but epsilon naught was like 8.87 times 10 to the minus 12 or something like that, right? So 8 whatever's times 10 to the minus 12. Did I even bother to write this one down? I did. No, I didn't. Did I do it here? Of course not. Did I do it here? No. See, I don't like knowing things because it hurts. Where did I write down mu naught? I didn't write it down anywhere. I know how it starts. I just don't know what exponent it goes to. Oh, come on. -7. There we go. I just couldn't remember what the exponent was. Mu naught. Okay. You promise not to freak out, right? Yeah. You promise to be okay? Because I'm going to let you know later why this number is what it is. But it will be profoundly disturbing. And I'm not joking.
I will not make promises I can't keep. I'll freak out inside.
Mu naught is 4 pi times 10 to the minus 7 henries per meter. We'll get to henries later. Yeah, henries per meter. Okay, we'll just say in SI units. Okay. Where? No, it says in SI units.
In SI units, okay.
Yeah. It's not a bird or a sparrow. Okay. Why is this number profoundly disturbing?
Units, that's all. I don't know.
Well, besides the unit. Units aren't disturbing.
So where is 4 pi coming from?
It's the 4 pi. All other constants, if you've been in chemistry and you've looked up constants, all the constants we've given you in physics up to this point, gravitational constant, 6.67 times 10, blah, 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 right? In whatever sig figs we can measure it to, right? Is always some like approximation, isn't it? it goes out to a certain number of significant digits, and then we hit the limits of our ability to measure, right? And we have to stop. What is the precision of mu naught? How many significant digits does it have? All of them. It is exact.
So that means. Can I just cross them out and make it one?
We don't even know that.
That's not the constant.
Wait, 4 times
12.7 something, 12.17, 12. I don't know. It's 12 something. But why is this unsettling? Well, I'm going to tell you the answer later. But on the surface, it should not be this exact. In a random universe,
Well, didn't he make the?
What if that's the only way?
are we in a simulation? Did we prove the existence of God? Like, what the heck is God? No. The answer is no to both of those. Okay? Not that those don't exist, but we can't prove it scientifically, right? But there is a reason why that is exact. And we'll get to it. And you'll be disappointed when we finally get to the reason. But it is a little bit creepy. Okay, we put it off long enough. What the heck is going on with that cross product? Okay, what's our hat? It's a unit vector pointed in what direction? The R direction. But you know what we're going to do with this. Instead of our hat, how are we going to write this down? R vector, and then we'll pick up like an R cubed in the bottom, right? So the R squared in the bottom feels a little bit familiar, right? Everything kind of goes as an inverse square law. That's what electric fields do. That's what Coulomb's law does, right? That's okay, right? ds. What's ds? Well, it's obviously the thing we're integrating across, right? But ds in your book is like dl in my brain. It's S is a generic like distance thing, right? And so we have a current, right? And what are we doing with that current? Chopping it up into little tiny length pieces. Remember, it's silly, but current is not a vector. Do you remember how we did the force is equal to IL vector cross B for the force on the wire? And I was like, yeah, it's stupid, current's not a vector, but really what's our vector direction? It's the direction of the current, right? Same sort of things going on here, right? That ds, the direction of ds is whatever direction the current's going, right? It's just we're chopping up length, not current. Okay. This is called the Biot-Savart law. Yeah, it is the BS law, right? But unfortunately, it's correct. So what do we do to find the total field? We integrate the little tiny piece. The mu naught, the 4 pi, and the I all come out. And we've got to figure out the rest. The little tiny length of our wire. Okay? So, let's begin. We need a wire. And we need a coordinate system. So, here's my wire. We'll kind of do like a setup with the perpendicular bisector here. And what we're going to do is we are going to find the magnetic field at that point. That point is going to be a distance A away from the wire. we're going to find a little tiny representative piece of this wire. The current is flowing to the right. And so that means our ds vector points which way? To the right. Like I said, we follow the current, right? So the current's all along that wire. It's flowing to the right. And so my little tiny piece of the wire, which I'm now going to call dx, is that okay? ds is dx in terms of its magnitude and, well, frankly, its direction, okay? So we're going to be integrating from the left to the right across the wire, trying to figure out. And so what we're going to do is we are going to find the magnetic field from that little tiny chunk that I've outlined right there at point P. Once we've found out what that is, and we've taught the integral how to do it, right, in terms of x, we'll just let the integral run, right, all the way along that segment of wire. All right. So, I mean, I guess the good news is that you don't have to go figure out the little tiny chunk, right? The little tiny chunk is given to you. The bad news is you now have to integrate a cross product. How do you integrate cross products? What was that? Oh, I thought you said cheat. Yeah. That's exactly what you do. You don't cheat. What you do is you avoid it. Well, you give it to a mathematician, let them have fun with it for a while, and then you pull out the useful bits, okay? Because the mathematicians will come up with a lot of not useful bits, right? But then there'll be something in there that's useful. Now, we can get rid of the cross product, can't we?
If you say so.
Lewis, I know people. I can get rid of things that bug me. You're good. You should trust me. You should trust me because I know all the right people. All right. So, how do you get rid of a cross product?
You do it?
Right hand rules. Right hand rule is going to save us. Because if we take this cross product right here, this ds cross r, I can write ds cross r, I'm going to do r vector now. Okay. This is going to, okay, well, no, wait a second. Yeah, I want to do that. ds cross r, its magnitude will be what? I didn't ask a hard question. What's a cross b?
AB.
It's AB sine of the angle between them, right? So it's A ds times r vector, magnitude, times the sine of the angle between them. Okay. What's that angle? That angle is theta, isn't it? Not 90. Not, well, kind of looks 45 here, doesn't it? But what if we're on this end? What if we're right underneath it? What if we're over here? The angle's like this now, right? 90 there, getting smaller on this side, right? As we integrate across this wire, what is that angle going to do? It's going to change, isn't it? Theta is our changing thing, isn't it? Okay. So I got rid of it like that, but what about direction? Let's handle that later. Let's just deal with that later. Okay? Let's focus on working out the magnitude of this integral. Oops. Forgot to put my vector sign over there. Okay. So what does that mean? I can now write this integral as mu naught I over 4 pi. Integral ds times r times sine theta all over r cubed. Where did the r cubed come from? Yeah, when I started using r vector, right? Okay, instead of r hat. Okay, so what's going to happen with the r on top and the r cubed on the bottom? We're going to get rid of one of them, right? So we get an r squared. So, okay. Okay, it's okay. How is the vector r, which is my starts where my magnetic field starts, and end where at the point where I'm trying to find it. None of that's changed from our original direction of r. What's the relationship between r and theta? Here's r. Here's theta. And I want this component and this component of r. Yeah, okay. It's r cosine theta on that side. And it's r sine theta on this side because it's not touching. And so that means that I can write my r vector as r cosine theta I hat plus r sine theta j hat, right? The way I've drawn it here is it's pointing to positively to the right and positively up as I go over and as I come up to this point. Okay, fine. Be that way, right? Okay. I still don't know what I'm doing with my ds. It becomes a dx, doesn't it? Okay. What the heck have I done here? I got my thetas. No, I've got my r in terms of theta. I have, can I write this ds as dx? Okay, got that. Dx sine theta over r squared. Okay, so I've got my r vector. Yeah, it's bad. You have to trust me. Lewis, do you still trust me? Not anymore? Not anymore? Yeah, I don't blame you. Just trust me that this is the way you want to go. We're gonna turn r into theta. We're going to turn r's and x's and everything's into thetas. Why are we going to turn them all into thetas? That's the thing that changes, isn't it? As we march along this wire, theta starts like small, gets bigger, goes to 90, and then decreases again, right? As we go along the wire. So if theta is the thing that's changing, I've got to get this thing into the language of theta. And this is how I'm going to do it. I'm going to kind of come back over here, right? And I'm going to take a look at a triangle that is being formed, right? So I can write down the sine of theta. What's the sine of theta in this triangle here? It's a over r, isn't it? And then I can write down the cosine of theta. What would that be? For this triangle right here, what's the length of this side? I mean, I know it's our cosine, but like, it's x, isn't it? It's not just dx, it's x, isn't it? However far away we are, right? It's just whatever distance we have here, isn't it? But the problem is, this is where x equals 0. So if we're over here, the cosine of theta is negative x over r. And for good measure, what's the tangent of theta? The y, a, over negative x. Yes, okay. So, this is equal, well, let's see. R is now equal to A over sine theta, but physicists hate fractions. So what's the inverse of the sine?
Oh god, a cosecant.
It's cosecant. And I can solve, let's do this one because it doesn't have any r's in it. X is going to be equal to negative a cotangent of theta. Where'd the cotangent come from? Divide by tangent, but then I can make a cotangent, right? So where does this get me? Ooh, it gets me a crash. What's going on? Safari was updating. Yeah, we're done. No, we're not done. We got 15 more minutes of this hell. Where were we? We were right here. Okay. So, now that I've got those, can I find my dx? Oh, no.
Derive both sides. A cosecant squared. It'd be negative cosecant, so yeah. A cosecant.
Right? Isn't the derivative of the cotangent the cosecant? This becomes a cosecant squared of theta d theta. Yeah, because the derivative of cotangent is the negative cosecant squared. Okay? Let me throw you a life vest right now. Okay? Because what's going on right now is I have thrown you in the icy water and I'm holding you down underneath, right? So now I'm going to let you bob up just a little bit. I'm going to throw you a life vest. Okay? We only have to do this once. You will not have to do this ever again. What we get at the end is what's going to be really, really important. Okay? So we're getting there. But don't panic. Don't panic. You panicking?
I just have a question.
Yeah.
So like this is for the side where you have negative x, but we have to multiply it by 2.
We'll get there. We'll get there. Okay? What have I got now? I've got pieces, parts all over this screen of various things, right? There's just a lot of parts everywhere. So let's see if we can get them all. Avengers assemble into one piece. Okay. What is my dx? It's a cosecant squared theta d theta. So that's my dx, right? My r's gone. I've got a sine theta that still is along for the right up there. And what's my r? Oh, a cosecant theta. But we, B.O. Savar knew what he was doing. So that one goes away. One of the a squareds goes away, right? But the cosecant squared theta definitely goes away, doesn't it? So what am I left with?
Sine divided by a.
Mu naught I over 4 pi a. Why? Why does the a come out?
A is a constant.
It's a constant, not doing anything. Integral of sine theta d theta. From what to what? From wherever we start to wherever we end. Right? What's the integral of sine theta? Cosine theta with negative sign. Okay? So this turns out to be mu naught I over 2 pi a times the cosine of theta 1 minus the cosine of theta 2 because of the stupid negative sign that's in there. 4. Because I can't read. There it is. This right here is the answer. It's equal to 42 or the square root of 2gh. No. Yeah, what the heck were we looking for? The magnetic field around a current carrying wire. We would have to express the length of that wire in terms of these angles, but we'll get there in a second. Yes?
Cosine theta 2.
No, because there's a minus sign.
Oh, yeah,
And it's a negative. I skipped some steps there because I was getting tired of writing math.
So if it was negative cosine,
And I was running out of room.
wouldn't it be negative cosine theta plus?
Uh-huh. Do it on the paper and you can see what happens. Yeah. Okay. So let's get some thetas in here now, right? Let's get some thetas in here. Okay. Right hand rules. Let's talk about thetas. Let's see how bad the audio is going to screw up. Come on. Technical difficulties. Here we go.
Electric current flowing through a long straight wire produces a magnetic field that circulates around the wire. But how does the strength of the field depend on the distance from the wire? If a tiny segment of electric current could exist,
Which it
it
can't.
would produce a magnetic field proportional to the inverse square of the distance.
Okay. Good with that.
The direction of the field is related to the direction of the current by the right-hand rule, or the
Okay,
vector
we'll get
cross
there.
product. The field would be biggest when the current segment and distance vector are perpendicular. But electric currents can never exist in tiny segments. So any real magnetic field must be found by adding up or integrating the contributions due to each segment of a flowing
Integrating
current.
along, making that blue one bigger.
The field, due to current flowing in a long straight wire, is always perpendicular to the wire and decreases as the inverse first power of the distance from the wire.
Okay, watch.
The net result is a field that goes in circles. The lines of force are circles consistent with the wire, and the field is the same all the way around each circle.
Does it depend on where I'm standing? Starting to wonder. Where did they get the circle? It's not the recording. Where did they get the circles from? I thought we were finding the magnetic field at that point. Well, you can't have a little segment of wire. A current must exist as a long, right, set of things, right? But weren't we just finding it at one spot? No, we want to find it everywhere in space. So what we just did was just for one point. But if you take that one point at that distance, and then you kind of go to a different spot at the same distance, what's the answer going to be? Same magnitude, tangential direction. They did a little right-hand rule there, right? And if you carry that around, you're just going to get circles, which is what we saw in the iron filings, right? The iron filings had those circles coming out. So we get this picture right here. And if we take our result, right? We had mu naught I over 4 pi a, and we had cosine theta, what was it, 1 minus cosine theta 2. And remember, it was a wire, and we had this distance a from it. And like we started over here, here's theta 1, and then theta 2 was going to be over here, right, as we went. If we go for an infinite wire, meaning it stretches to infinity, negative infinity on one side, stretches to positive infinity on the other, what will theta 1 be? Theta 1 will be equal to 0 degrees. And what will theta 2 be equal to? 180 degrees. So now, for an infinite wire, remember infinite is just however long it needs to be infinite. Okay? We get mu naught I over 4 pi a times the cosine of 0. What's the cosine of 0? 1. Minus the cosine of 180. Not 1. Negative 1. Lewis, there's your 2. So what does this turn out to be? This turns out to be mu naught I over 2 pi a. You will often see this written as B equals mu naught I over 2 pi r, where r is what? It's not the radius of the wire. Eventually we're going to have to go inside wires. We're going to stay outside for now. Okay? But I like using the symbol A in this equation just to remind myself it's a distance from the wire, right? It's not the radius of the wire or anything like that. But it is common practice to write this as 2 pi r, where r is not a radius. R is a distance from the wire. So we have conquered, literally conquered, what I think is the hardest integral in this class. That one. There's a lot of pieces coming together, okay? The good news is that how many times do we have to do this? No more. If you go into junior level E&M, it's coming back, baby, right? But if you're not a physics major and you're not going into junior level E&M, you don't have to worry about BO sub R ever again. What you do need to worry about, though, is this. Because this is only a magnitude. How are we going to find the direction? Right-hand rules. We'll pick that up on Thursday. I will see you then. What?
So that is only for like infinite, the 2 pi. But it's only for the infinite.
Yeah, we haven't done a circle.